My name is Benton Hobson, and for my final project in heat transfer, I decided to do an analysis on one of my favorite superhero characters, the Flash. One of my favorite things about the Flash is that he can travel vast distances in a matter of seconds. However, this does bring up some concerns. If he is running this fast, would he not be producing an extreme amount of heat in these short amount of times? Also, does the velocity have an effect on how much energy he's producing? Would his energy increase with how fast he's going? For example, 200 miles an hour versus 600 miles an hour. Another thing I wanted to look at was environmental factors. If it's cold and snowy outside, would he produce more or less energy as opposed to if he were in a hot, dry climate? One of the first things I had to think about is how to analyze the Flash. One of the assumptions I made was that the Flash's body was made of nothing more than cylinders and spheres. Sphere for the head and cylinders for the body, the legs, and the arms. This will make calculations a lot easier later on in the presentation. Other physical factors I needed to be aware of is that in the comics, the Flash's top speed, or one of his top speeds, is Mach 3.3. However, in our class, we did not talk about how to handle objects that travel at such velocities, so I'll be saying below Mach 1. The energy balance equation is what helped me determine the surface temperature of the Flash. The energy generation term was calculated by multiplying 1/2 rho v cubed CD or C sub D A. This is how I found the energy output that he would be producing, and this would be dependent on his velocity and the density of the environment. Almost all values were able to be calculated by hand. In order to calculate the age, we first had to find our Reynolds numbers for each individual geometric portion of the Flash. So once each Reynolds number was calculated, we had to use the correct Nusselt equation, or the Nusselt correlation. The Nusselt correlation on the right is used for spheres. The one on the left is used for cylinders. Notice that in these equations, they are functions of Reynolds, Prunell, and mu sub s. All the values will be calculated at the film temperature, which is just the surface temperature of the Flash and the ambient temperature, and take the average of that. However, the mu sub s will be taken at the surface temperature of the Flash. Now, once all the Nusselt numbers are calculated for each individual geometric portion of the Flash, we can now calculate the heat convection coefficient, which is our H. And once we calculate all the surface areas, we can then plug that back into our equation found at the top. Now, because this was also an inseparable ODE, electronic help was used to solve our T-surface. I used Mathematica to help to solve for the surface temperature. After going through a couple iterations and using certain guesses as initial temperatures, or for the initial temperature, I eventually came to these values for 89 meters per second, 178 meters per second, and 286 meters per second, which is in miles per hour. That'd be 200, 400 miles an hour, and 600 miles an hour, respectively. Now, these temperatures were taken at certain time intervals because at these different at these certain times, the Flash would arrive at his destination in Idaho Falls quicker the faster he runs. So at the 89 meters per second, it would take him about 8 minutes to get to Idaho Falls. So this is the temperature after 8 minutes. For 178 meters per second, this is about a 4-minute run for the Flash. So that is the temperature he would what his surface temperature would be after 4 minutes. This following graph is a time versus temperature of the Flash traveling 170 meters per second. As you notice that after a certain time, if he were to run a little bit longer, he would reach very high temperatures for his body, which would be very concerning if you were to stop by any body of water, or if you were to run and stop right next to someone, they would most likely be incinerated or vaporized because of or at least get really bad third degree burns. It's important to note that going through solving in Mathematica the surface temperature, all the velocities follow this same curve, or in other words, to determine the temperature for the Flash all the curves follow these similar temperatures. However, at lower speeds, it took them a little bit longer to get to that plateau that you see at about 900, 800 seconds. The faster he were to run, the quicker he would get to those extremely high temperatures and reach that plateau. So now that we've seen that as he runs faster, he gets warmer, another thing I wanted to look at was to see what happens when the environment is taken into consideration. In colder temperatures, if we were to assume that everything is atmospheric, the colder the air, the more dense it becomes. So how does this now affect the energy output? Staying at a constant velocity and we increase the density, it is noted that that if we increase the density, the energy generation of the Flash actually becomes greater than what it would be at a lower density. So if you were to be running in Antarctica, for example, where it's negative 60 degrees Celsius, he would be producing or have to produce a lot more energy to run the same 200 miles an hour, or excuse me, the same 89 meters per second, the 178 meters per second, and the 286 meters per second. Conversely, if you were to be running, let's say, in Death Valley, where it is warmer and the density of the air is less, his energy output would essentially would be lower than what it would be in Antarctica. So overall, his temperature would be less running in a desert than it would be running in Antarctica.